All right, everyone. This is Anna Bergstrom at Boise State, and we are doing the final lecture here in our Redox module on Pourbaix diagrams. And acknowledge Nick Gubbins and Matt Ross at CSU for helping put this lecture together. So, our learning objectives for this are you should be able to describe a Pourbaix diagram and how it's calculated, and interpret a Pourbaix diagram for a given chemical species, and then potentially make treatment recommendations for pollutant removal based on these Pourbaix diagrams. So this is something that should be familiar to you. We've seen this in our carbonate sections on, this is what's called a predominance area diagram. And we could see that over a range of pHs, we have different carbon species, inorganic carbon species, that occur over this pH range. So again, when we're at low pH, we have mostly dissolved CO2 and carbonic acid, and then as we increase our pH, we can see that our bicarbonate dominates, and then finally at our highest pH, our carbonate dominates. So this is something that you guys should be familiar with, and then we can use kind of these similar concepts and roll them into Pourbaix diagrams. So a Pourbaix diagram is just a very specific type of predominance area diagram, and we have pH on the x-axis and redox potential, or EH, as you'll remember from previous lectures, on the y-axis. So a Pourbaix diagram here, this is simply for water. So across, again, we have pH on our x-axis, where we have more basic water over to the left and more acidic water over to the right, and our redox potential here. And we can see that we have these straight lines in a pretty narrow envelope in which we actually have water as a function of pH and EH. So if we have a more reducing environment, a more negative EH, we end up generating hydrogen gas. If we're in an extremely oxidized environment, really high EH and a lot and more basic, we can see that we end up with more hydrogen gas because we just don't have those, oxygen gas, because we just don't have enough hydrogen around, and we're in a really oxidized conditions. So this is another example, a Pourbaix diagram for copper. So pH here, we have very, very basic conditions over on this side, and moving into very, very acidic conditions on this side. And we can see that as we change our redox potential, we can move from copper 2+ in more oxidized conditions down into copper in more reduced conditions. And we can see frequently this will give you the species of, or if we're working with solid or dissolved species, depending on where we are in our Pourbaix diagrams. So why do we have straight lines on here? Well, EH depends on pH. Again, remember where this is true wherever our hydrogen ions are present, which is pretty much almost every location. And we describe these diagrams and calculate them using the Nernst equation. So the different components of the Nernst equation, we calculate EH using E naught, which is the potential of the reaction. V sub t and lambda are constants, and n is the number of electrons transferred in the reaction. And then you should all be familiar with this over here because we've used it a lot in this class. C and D are the reductive agents, and A and B are the oxidative agents. So here's an example of a Pourbaix diagram with selenium, and selenium can be a huge issue with water quality. Solid selenium here is something that can settle out of water, but if we are in more oxidized conditions, we might have selenium that can stay dissolved here. So if we have selenium issues where we have selenium dissolved in water, and again, this can get into food webs and cause huge animal and human health issues, and we might want to turn our selenium into solid selenium. What will we do? Well, chances are we could lower the pH a little bit. That might be one option to move it in this direction, but we also probably have to change the redox potential. So in the case, some ways that people treat selenium issues is they can do stuff like put selenium streams and have them flow through wetlands, or returning into more reduced environments, and then we would move the selenium into sort of this envelope where we are more likely to have solid selenium, and that can settle out. So here's a case study. As we've looked at some across all of our classes, is this issue of acid mine drainage and iron, particularly in mine drainage. So the stream on the left is clouded with iron hydroxides. This is this red material, the solid red sediment that's settling out in this particular stream, and managers might want to clear this stream up. So what would they do? Well, what you might want to do is look at a iron Pourbaix diagram. So here, these iron oxides that are settling out in the water are somewhere in this space here. And if we are in the iron 2+ realm, this is where iron can be dissolved in water, and it would clear up our issue. So one thing to note here is our iron 2+, you'll notice this is actually at lower pHs. And so if you are immediately downstream of a mine adit that's draining acid mine and might have a lot of iron in it, you might not know it might appear clear because all of that iron is in this dissolved iron 2+ form. It's not until you go a little bit further downstream where you might have this more oxidized iron form that's then causing these solids in your stream. So you have a number of options to deal with these solid iron oxides. You can either lower the pH or you can change the ORP here. So what are we going to do? Our options are to introduce strong oxidizers like dissolved oxygen, which is effectively climbing back up the redox ladder, or we could introduce protons, so we can add acid and change our pH. So to wrap it all up, I think we've shown here that we can use Pourbaix diagrams to inform our management decisions and how we treat some water quality issues. So you should be able to use those to figure out which direction you need to move in order to improve a certain situation. And that wraps up our Redox module.